Welcome back to your custom deep dive. Today we're looking at a tech spec sheet from HDTV Supply for the Kramer VM-2D distribution amplifier.
Yeah, and it's a really fascinating piece of hardware to unpack. I mean, I'm glad to be here to break this down with you.
Right, so imagine you're staring at this absolutely pristine 4K video feed. The colors are deep, the resolution is flawless, and you need that exact same image perfectly mirrored on two separate screens across a massive room.
Which sounds easy, right? Like just grab a cable, slice it open, and splice the wires in two.
Exactly my first instinct. But with modern digital signals, doing that is just a guaranteed way to get a completely blank screen. So we're unpacking the physics of how professional hardware takes a massive data stream and splits it without losing a single pixel.
And you know, the scale of that data stream is really staggering. We are talking about a DVI signal pushing up to 10.2 gigabits of data every single second.
Wait, 10 billion bits a second.
Yeah, exactly. Down two different copper wires.
See, that is exactly where my brain goes straight to plumbing. Like, if I take a garden hose and put a Y-splitter on it, the water pressure just immediately drops in both hoses.
Right, the pressure basically cuts in half.
Yeah, so if we're splitting 10 billion bits of data, doesn't the digital pressure drop? Like, how are both screens not getting a degraded, fuzzy signal?
Well, to understand that, we have to look at what actually happens to a digital signal as it travels down a cable. In a perfect world, digital data is a series of crisp, square waves.
Just clean ones and zeros.
Precisely. But copper wire has physical limits. So over distance, or, when you try to physically split the current, cable capacitance basically smears those waves.
Just smears them, like literally.
Yeah, the sharp, clean corners of your square waves turn into these mushy slopes. And on top of that, the timing gets sloppy, which engineers call jitter.
So the receiving monitor looks at this mushy offbeat wave and just has no idea if it's looking at a 1 or a 0.
Right, which is why this Kramer device isn't just a simple splitter. It uses a mechanism called equalization and reclocking.
Reclocking. Yeah, reclocking with a K, actually. It intercepts those degraded, mushy waves, and instead of just copying them, it actively reads the underlying 1s and 0s. Oh, so it's not splitting the original signal at all.
No, not at all. It creates a brand new, perfectly timed internal clock cycle and rebuilds those crisp square waves from scratch before sending them out to the two screens.
Wait, really? It's basically reading the blueprint of the original signal and building two perfect brand new replicas in real time.
Exactly. It acts as a real-time digital regenerator. And it supports all the high-end stuff, too, like deep color, 3D, and Dolby True HD audio.
That is wild. But rebuilding the physical wave is really only half the battle, isn't it?
Oh, definitely.
Because even if the 1s and 0s are perfectly crisp, the video source and the two displays still have to actually agree on what those 1s and 0s mean.
Right, they need a common language.
Yeah, like if I plug my laptop into a 4K projector and an older 1080p monitor at the same time, my graphics card usually just panics.
And that panic is a failure of what's called EDID, or Extended Display Identification Data.
EDID. Okay, what does that actually do?
Think of EDID as a digital handshake. It's a tiny file on every monitor that basically says, here's my resolution, here's my refresh rate, here is exactly what I can handle.
I see. And if a video source tries to shake hands with two totally different monitors at the exact same time, it doesn't know whose rules to follow.
Which is where the software inside this amplifier comes into play. It has an intelligent algorithm called IED Pro that acts as a diplomat.
A diplomat, so it's negotiating between them.
Yes, exactly. Instead of letting the source device blindly negotiate with two screens, the amplifier sits in the middle. It reads the EDID profiles of both connected displays, calculates the optimal common denominator, and then reports back to the source device telling it exactly what to output.
Oh, wow. So you achieve actual plug-and-play. The source device thinks it's talking to one perfect monitor, and the two actual monitors get exactly the format they need without crashing.
Exactly. But, here is the physical vulnerability of pushing 10 gigabits a second.
Right. The hardware itself.
Yeah. You can have the most perfect signal regeneration and the smartest diplomatic algorithms in the world, and it all goes out the window the second someone trips over a cable.
Oh, yeah. Like during a critical presentation. If a connection gets loose, you don't just get a fuzzy picture anymore.
Right. You get a total drop in that digital handshake we just talked about.
So how does this little aluminum box handle that?
Well, that's why the chassis uses lockable wiring connections. You actually physically secure the cables into the housing so an accidental tug won't disrupt the stream.
And it's completely silent too, right? Because it's fanless.
Yeah, it relies entirely on convection cooling. The aluminum enclosure acts as a heat sink, silently dissipating all that thermal load without a single moving part.
That is incredibly clever. So for around $404, you're getting a device that serves as a real-time digital regenerator, a software diplomat, and a silent physical vault for your data.
It really is all of those things. And actually, I want to leave you with a final thought to mull over today.
Oh, I love these. Lay it on us.
So, if this level of sophisticated algorithmic translation and physical wave rebuilding is required just to perfectly mirror one single video player to two screens, consider the sheer scale of the outside world.
Right, because we see screens everywhere now.
Exactly. Think about the massive invisible network of thousands of these translators constantly working behind the scenes. They are processing and rebuilding signals every microsecond, just negotiating millions of digital handshakes.
Just to power the giant video walls and digital landscapes you walk past in airports and stadiums every single day.
Precisely. It is a massive invisible infrastructure.
It really completely changes how you look at a multi-screen display. The next time you see a pristine 4K video perfectly synchronized across a massive wall, you will know exactly the kind of physics and diplomacy making it happen right behind the scenes.